by tycho, by the way, in case you were wondering. So in a dipole moment, you've got two charges where the vectors are pointing in the same direction, so they sum. And the way to figure out the dipole moment is to just take the one of the charges and multiply it by the distance between them. And I'm sure there's a different method for if the charges are not equal, but we haven't gotten into that so far. And in biology, I'm learning about transcription. So we're talking about DNA and how it is chemically structured and how that chemical structure yields its function. And then the RNA is a little bit different, or a lot different. So it's way more reactive and less stable. So in DNA, you have nucleotides that are the monomers of DNA, and they polymerize through condensation reactions. And that's what builds up the DNA double helix structure, so the double-stranded structure. So in a nucleotide, you have nitrogenous bases, you have the deoxyribose sugar, and you've got the phosphates that make up the backbone. The sugar and the phosphate makes up the backbone of the DNA. So you've got like hydrogen bonding going on between the nitrogenous bases, which build up, they're nonpolar, and so they create hydrophobic interactions, which create more stability in the DNA structure. And then the sugar phosphate backbone is hydrophilic, and that's why it dissociates in water, because it's made up of those sugar and phosphates. So in a hydrolysis reaction, it'll break up into monomers. And in between the stacking of the sugars and the nitrogenous bases and the phosphate layers, you've got van der Waals interactions, which create even more stability in the molecule. And in this way, DNA stores information because it's really stable, so it takes a lot of energy to break it apart. But there is a mechanism for unzipping it, and I'm running out of space on my phone, so I'll have to get into that in another video. But they figured out this double helix structure from X-ray crystallography. Isn't that really cool? I think it's really cool. And they shoot X-rays at this molecule, and it refracts or bounces off the electrons and lands on a surface in the back that shows you the angles in the bonds between the chemicals in the monomers in DNA. And they saw that it was 0.34 nanometers, 0.2 nanometers, and then 0.34 nanometers again. And that angle is what allowed them to figure out that the complementary base pairs were what made up the structure of DNA. So purines were bonding with pyrimidines, and it was not purine to purine, and it was not pyrimidine to pyrimidine, because they would be too close or too far away from each other to get the angles. And they said the most underrated statement of all time, which was that it has not escaped us that this structure can be copied. It wasn't until later that they figured out how the structure is copied, but I think it's really cool that they put all of that together with just X-ray crystallography. It's pretty complex, but also really awesome. Okay, have a good day.